Moveable pulleys. First, let's define what a movable pulley is. We've already dealt with the fixed axis pulley. That's where its axis of rotation, which is its axle, did not change relative to the ground or other stationary reference frame. In other words, the pulley didn't move. Another name for movable pulleys is called traveling pulleys. For the fixed axis pulley, the rope moved, the load moved, but not the pulley. So what could a movable pulley do? That's kind of a simple question. It can move. It can move up or down, and it will take the load with it. So let's look at this picture here. There are two systems of multiple pulleys. Okay, the reason I say multiple is you can see, let's look at the bottom here. You have rope coming down like that for the guy on the left, one coming down in the middle, one coming down in the right. So there's actually three pulleys there. So let's get rid of that. Which is the fixed pulley and which is the movable pulley? And just one more hint. See this loop here? This is where you'd hook on some kind of load right at the bottom. And you'd be pulling on this rope and that would lift the load up. So which is fixed and which is movable? The top system of pulleys, right over here, that's attached to the boom. Okay, you can see this clamp here. And it's fixed. It's not moving relative to the boom or the ground. The lower system down here, that also has three pulleys, and this will actually move up when you pull on this rope, and if you let go of the rope it will move down. So there are our movable pulleys. Here's a schematic of fixed and movable pulleys that will be used to lift the mass at the bottom, this mass here, by applying the force over here on this rope, the applied force. A and C are fixed, right here they're let's say they're stuck to a ceiling. B will move up and down and it will travel with the mass. So your continuous rope looks like this, and then this here hooks maybe into the center of the pulley here to pull the whole thing up, in addition to this moving it up also. So this rope is fixed to the pulley. We want to find the required applied force to lift the mass M. Now clearly, if we were just lifting this on our own, we would need mg. But we have this pulley arrangement. Let's see what that gives us. We're going to use free body diagrams to figure out the required force. First, before we move on, label this picture with all the forces that you can think of. And remember, we're going to deal with massless pulleys and strings, so you don't have to worry about rotational motion or the mass of the rope and what that does to the problem. Here's the forces I came up with. Okay, we of course have our applied force. Somebody's pulling on that rope. We've got gravity pulling down on the mass, and that's the only mg we have because we've assumed massless pulleys and massless rope. Let's see, we have a tension force here for this piece of the rope. We're going to call this tension 3. This is tension 2 holding that pulley up to the ceiling, and you can see the rest of them. I'm not going to read each one, that would be a little silly. And now hopefully we're going to find that some of these tensions are the same so we can reduce the amount of variables we're dealing with. I forgot to mention you were supposed to draw the free body diagrams for each one of these pulleys. It was written there, hopefully you saw it. And if not, back up before you look at these free body diagrams and give it a shot on your own. So we've labeled the pulleys A, B, C, and we've also got the mass, M. So here's the free body diagram for the mass. You just have mg going down and tension 4 going up. And I'll just take one of these and talk about it in a little detail. Pulley B, the traveling pulley, it doesn't have mg acting on it, does it? No, it has tension 4 right there. And then it has three tensions pulling it up, T5, T7, and T3, and that shows there. And I'm not worrying too much about the size of the vectors, but if you're in equilibrium, you can imagine these three guys have to equal this one right here so it's not moving. But don't worry too much about it. The directions are the important thing and just a rough idea of their magnitude. Well, fortunately, we're dealing with a massless string or rope and frictionless pulleys, so we can say that this force here is transmitted through this tension around the pulley to this tension force, around the pulley to here, to 5, and then finally to T7. They are all equal because the string, it's not stretching or compressing. It has no mass to consider in the free body diagram, and the pulleys have no mass, nor do they use any energy in the rotation because they have no mass, and we'll cover that later in rotational motion. So the tension is everywhere the same in the string or rope. We could go ahead and replace all those forces with just one F, but let's leave our T1, T3, T4, etc. It's good practice. And we'll assume the mass is stationary, which means it's not accelerating, right? Stationary, you have A is equal to 0. And write Newton's second law equation for each of the 4 free body diagrams. The equations are on the next slide. Try them yourself first. We'll start again with the mass because that's the easiest. You just have the tension force in 4 minus mg is equal to 0 because it's not moving. And then let's pick another one. Let's pick B. You've got 3 forces in the up direction, T3, T5, and T7. T4 in the down direction, so it's negative, and that also equals 0 because nothing's moving. And you can do a similar thing with pulleys A and C. We actually need only 3 of these equations because we stated earlier how all these tensions are equal. And that's this line right here. And they're all equal to F_ap. And then what are we doing with this one? Who's this free body diagram from? Yep, B. Is that it? Yep. So what we're going to do is for each of these tensions, replace that with what? We're going to replace that with F_ap because they're equal to F_ap. So there's 3 of them. So we have 3 F_ap. And who else do I have here? I have tension 4. And that's the line that is directly connected to the mass. So I have the tension in this segment here, 4, is equal to 3 times the applied force. And then I will put that into our second equation over here. You know what? Let me erase that just to make that clear what's going on. Okay, this is now going into this equation here. And we come up with 3 times the applied force is equal to mg. So one more step, we just divide through by 3, and we find that the applied force is 1/3 of the force due to gravity acting on the mass. So what does that mean? It takes only 1/3 of the force to hold mass m stationary than if it was just being held up by one rope without a pulley. Or of course, if I had the mass here and it went around a pulley, a fixed pulley that just redirected the motion, you would need to exert a force of mg to keep it in the air. Now, you just need 1/3 of that force. We've multiplied our force, haven't we? This is similar to the window cleaner problem in the last chapter. Less force is used, right? F_ap is just mg over 3 to lift that mass, but it is used over a longer distance. So the work required to lift the mass is the same, whether this system is used or if the mass is just lifted up with one rope like that. Because if the mass is lifted a distance of delta y, right, this goes up a distance delta y, each one of these ropes attached to the traveling pulley are also moving up delta y. So the total distance that the rope is moving is 3 delta y. So when you multiply that distance by the force, right, 3 delta y times F over 3, you can see how the 3 cancels. The total work done is F delta y, just like if you used one rope to lift the mass. This now leads to the concept of something called the ideal mechanical advantage. And the word ideal there is we're assuming no friction in this problem. And the ideal mechanical advantage is going to be the force required to lift the load directly, so in this case that would be mg, divided by what force you're really using because you have some kind of configuration here. So in this case, we've got mg, that's the load, and F applied we calculated was mg over 3, and we get 3. We get an ideal mechanical advantage of 3. A simpler way to calculate this, and maybe you picked it up when you were looking at the picture, is just count the number of rope segments that are connecting to the load. So in this case, they're all going through the traveling pulley, which is connected to the load. So your mechanical advantage, your ideal mechanical advantage would be 3.